Before watching this lecture, you should know about the standard normal distribution and the shape of the probability density function. You know, this bell-shaped curve that the PDF has. We'll extend that to the normal distribution, which is actually an entire family of distributions, and this family is the most important family of distributions in probability theory. So remember the standard normal distribution, which has this particular form of the PDF. So we write it like this. X follows a standard normal if the PDF has this precise shape, which is this function f of x 1 by square root of 2 pi e to the minus x squared over 2. This is the expected value. So that means that the standard normal has a expected value of 0. This is the variance. The standard normal has a variance of 1. So the standard normal is actually just one distribution in a family. And the family of distribution is denoted by x follows a normal distribution. We use a parameter mu to represent the expected value, and we use the parameter sigma square to denote the variance. So this thing here is what's called a two-parameter family. There's actually an infinite number of normal distributions. One of them is the standard normal. So normal 0, 1 belongs to the family of normal distributions, but so does normal 0, 2 with the variance of 2, normal 1, 1, and so on. You can have any real number for mu. So mu must be any number between minus infinity and infinity. And sigma square, being a variance, can of course not be negative, so that can be any number between 0 and infinity. So not just integers are allowed here. It's really nice to be able to plot the probability density function for an arbitrary normal in many cases. That is, we want to make like a similar plot to this one, but for another normal distribution in the family. And the software I would recommend is Maple for this. It's really good at dealing with random variables, or decent at least. So to work with random variables in Maple, you have to start by telling Maple that you want to use one of its packages, and that's the statistics package. And to do that, you use the command with. So with statistics, like this. And Maple is very, very sensitive to exact notation, so you have to use the upper lower characters correctly, and you have to use a colon that implements the statistics package. So once we have done that, we can create random variables in Maple. So let's use capital X like we've done before. We need to create this random variable, so it's really important that you do colon equal to. Equal won't work. Then you type random variable exactly with these cases, and inside the parentheses you tell Maple precisely what random variable you want to look at. So let's begin by looking at the standard normal. So it uses the same notation that we have used, so it uses this n for the normal, then it starts with the expected value, and the standard normal has expected value 0. and then comes the variance, so we put a 1 here and parentheses. So we now have an error, and I forgot it doesn't use n, it uses normal. So you have to type random variable normal 0 1. The response you will get is actually the range. So the range of the normal distribution is all of R. So once we've done that, we can do a lot of things. We can play around with this random variable, plotting the PDF, plotting the CDF, figuring out the expected value, the variance, and so on. So let's just look at some of them. So if you want to know what the PDF of this random variable is, you just type PDF with capital letters, the name of the random variable, and the variable that you want to use in the function. So we can use small x for that, like we have done. So here is the formula. Maybe it looks slightly different from the one we put up here, but it is actually the same. Square root of 2 over 2 is 1 over square root of 2, so it is the same. You can now plot it by just using the plot function as before. So if you do plot, and we want to plot the PDF, x, use the small variable x, then the range that you want to plot, say from -3 to 3, then you get this bell-shaped curve for the standard normal. You can also plot the CDF function. So just change the PDF to the CDF. Remember, that was the cumulative density function. That gives us the probability of getting a number less than or equal to small x, and that looks like this. It's an increasing function, as we would expect, going from 0 when x is very small up to 1 when x is very big. You can find the expected value and the variance of random variables by using the function mean. We know that the standard normal has an expected value of 0, so we can confirm that. And you can use variance, and that should be 1 for the standard normal. And you can calculate any kind of probabilities from the standard normal by just integrating the PDF. So let's say I want to know the probability of getting a number between -1.96, almost, and plus 1.96. Then I just replace f with the PDF, x comma x, and I integrate over x. So that will be the area under the PDF curve, and we know that that should be approximately 95% for the standard normal. So let's just go back, because we can do exactly the same thing for any random variable in a normal family. So if I want to do, let's say x is a random variable with expected value 2 and variance, let's say 0.5. I want to know what that looks like. Then the PDF will be much more complicated, and we don't need to get into exactly how the PDF looks like for an arbitrary normal distribution. We can plot the PDF. Now in this case, the expected value is 2, which means that the PDF peaks at 2. So it's probably better to make the range such that 2 is somewhere in the middle. So if we do like -1 to 5, then it will be in the middle. This has a variance of 0.5, so that's why it's a little bit taller and thinner. We can find the mean of x, which is 2, and we can find the variance of x, which is a half. Well, surprise, surprise, it's not the half, it's a quarter, and that's because what I told you to begin with is not quite true. When you define the normal random variable in Maple, it's actually here you put the expected value like we said, but this the second number, is actually not the variance in Maple. Here you put the standard deviation. So I have actually here created a normal distribution with a standard deviation of 0.5. The variance is the square of the standard deviation, and the square of 0.5 is 0.25, and that's exactly why we got 0.25 here. So if you really want to create a random variable with the variance of 0.5, then you have to put the standard deviation here, which would then be SQ. Well, let's use the square root symbol, it looks a little bit better. You have to use the square root of the variance. So if I make it like this, then it will create a normal random variable with the variance of 0.5. It's a little bit unfortunate, this notational difficulty with the normal distribution. Some authors like to put the standard deviation as the second argument, and some authors likes to put the variance as the second argument. You just have to be a little bit careful there. So if we go back to that and do all of it again, the mean, and now we get the variance of 0.5. We can calculate probabilities just like before by just integrating. Sometimes it's also nice to be able to plot two different PDFs in the same diagram so you can see the effect of changing one of the parameters. So here I've defined a random variable x. Let's take that back to the 0, 1, the standard normal, like this. Then what I can do is I can just simply create a new random variable. So let's create a new one, y, which is random variable, and let's create it to be a normal but with expected value 1 instead. It's not a standard normal, like this. Then I can plot the PDF of these two random variables in the same plot by just doing plot. If I want to plot two things in the same diagram, I need to put the functions inside curly brackets. So I can do PDF of x comma x. That's the PDF of the standard normal. Then I can do the PDF of y. And now I need to type the same variable here so it actually goes along the x-axis. So y comma x, and that, and let x go from, let's say, let's do -4 to 4. And that way, and of course you have to type the x equal to. That way you can actually see what the PDFs look like side by side. The first one, the kind of burgundy one, that's the standard normal. The next one is the normal distribution with expected value of 1. So it has simply, the PDF of that one is simply the same as the PDF of the standard normal, just shifted one unit to the right. So it has an expected value of 1. They have the same variances. So they have the same height and the same width. So I think the statistics package is a very useful tool if you're learning probability theory. So let's just summarize a couple of notes from the normal distribution. So if x follows a normal distribution and it has an expected value mu and a variance sigma square, then we are going to use this notation. And again, just be careful because some authors would actually use the notation normal mu sigma instead of sigma square, putting the standard deviation as the second argument. The normal distribution has a property that's very unique, and that's the following. If you take a linear combination of a normal distribution, if you take a linear function of a normal distribution, That is, if you create a plus b times x, that new random variable will also follow a normal distribution. And you can find the expected value and the variance according to previous lecture on how to find the expected variance and the expected value and the variance of a linear function of a random variable. So important property is this. Keep in mind that this does not hold for all random variables. So if you have a random variable following another distribution, one of them, let's say chi-square, then taking a linear function of that will not follow a chi-square. But for the normal, we can always know that the linear function is normal.